Hello friends, dear learners and my dear student. First of all, I take an opportunity to welcome you at my TYBSc Analytical Chemistry class. Friends, I am Dr. LABHADE, working as Associate Professor in Chemistry at KTChem College, Nasik. Student, in previous lecture we discussed the principle of liquid-liquid chromatography by using a matchbox model. In today's lecture we discuss what is theoretical plate, what is height equivalent to theoretical plate, HETP, how the number of theoretical plates or number of height equivalent to theoretical plates are determined, and finally what is the effect of this theoretical plate on the efficiency of chromatographic column. Student, we know that methods of chromatographic analysis are broadly classified into two types, that is a adsorption chromatography and second one is a partition chromatography. In adsorption chromatography, stationary phase is solid adsorbent and mobile phase may be liquid or it may be gas. In a partition chromatography, stationary phase is a liquid, mobile phase may be another immiscible liquid or a gas. If we consider the principle of adsorption chromatography, mobile phase, function of mobile phase is to carry the sample component into the or onto the stationary phase. Now in adsorption chromatography, the components which are carried by the mobile phase are selectively adsorbed on the stationary phase. That is differential adsorption process, that is a principle of adsorption chromatography. In a partition chromatography, when mobile phase carries sample component, on the basis of solubility difference, sample components are get separated. That means sample component which have more solubility in stationary phase, that will be taken first by the liquid stationary phase, while sample component have low solubility in stationary phase, that will be taken at the end of the column or sometime that may not be taken by the stationary phase. Therefore, solubility difference is a principle on which partition chromatography works, while differential adsorption process on which a adsorption chromatography is worked. Student, in previous lecture we discussed the matchbox model. With the help of matchbox model, we discussed the principle of liquid-liquid chromatography. In matchbox model, we know that there are a stationary phase and the mobile phase, and the sample components are separated on the basis of their, this is column first, stationary phase containing solvent first. This is a column second, mobile phase, and this is a solvent second. We know that when we place a sample component or a sample containing two or more components, when those are placed in this mobile phase, then depending upon the solubility, sample components are get distributed. That means here, if A is equally soluble in this both solvent, then 1/2 A is given in stationary phase and 1/2 A is given in mobile phase. Similarly, we know that B is 25% soluble in stationary phase and 75% soluble in mobile phase. Therefore, 1/4 A will be given, 1/4 B will be given in a stationary phase, while 3/4 B will be given in mobile phase. That means on the basis of solubility, these two components A and B are get distributed into the single box of this matchbox model. Now this is a stationary phase, this is a mobile phase. Though it contains two boxes, but here this is a single box in which these components are get distributed between the stationary phase and the mobile phase. Therefore, in chromatography, here each box represents a theoretical plate. Therefore, here this is a theoretical plate. Now it is clear that theoretical plate, that is a area of the column or a area of stationary phase that is utilized by sample component to undergo single distribution equilibrium. Therefore, theoretical plate in chromatography, theoretical plate is the height or area of the stationary phase utilized by sample component to distribute or to undergo a single distribution equilibrium. This area is called as a theoretical plate. Therefore, theoretical plate, that is an area of stationary phase which is utilized by the sample component for its distribution. Therefore, here in case of adsorption chromatography, stationary phase is solid adsorbent. How much area of that solid adsorbent is utilized by the sample component, that is a theoretical plate. In case of partition chromatography, stationary phase is a liquid. Therefore, how much amount or how much height of that liquid is utilized by the sample component to undergo the distribution. Therefore, here in chromatography, here theoretical plate, that is a height of column, that may be stationary phase or a mobile phase, utilized by sample component to undergo single distribution equilibrium. And therefore, here this area is called as theoretical plate. Therefore, theoretical plate, it is clear that it is an area of the column which is utilized by sample component to undergo single distribution equilibrium, that is between the stationary phase and the mobile phase. Height equivalent to theoretical plate, HETP. HETP in chromatography represent the height of that particular column which is utilized by that sample component to undergo that single distribution equilibrium. That means HETP is equal to the height of theoretical plate. Height equivalent to theoretical plate, HETP, means again the height of single theoretical plate or height of that column which is utilized by this sample component to undergo a distribution equilibrium. Now here we know that if the functional groups present on this stationary phase, if it is a adsorption chromatography, and if more number of functional groups are present on this stationary phase, then that more number of functional groups can hold maximum number of solid molecules on its surface. At that time, the height equivalent to theoretical plate is small. That means in a small amount or in a small area of the stationary phase, maximum amount of solute is get adsorbed. In such a case, the height equivalent to theoretical plate is small. But when number of functional groups on the stationary phase are less or few in number, then more amount of area is required to hold those particular molecules carried by the mobile phase. In that case, height equivalent to theoretical plate is more. That means here height equivalent to theoretical plate, it is again related with area utilized by that particular sample component to undergo a distribution. If mobile phase is polar, if solid molecule is polar, therefore polar molecules are get attracted on the polar stationary phase through a hydrogen bond type of bonding. In such a case, if more number of bondings are formed by the sample molecules with the stationary phase, then height equivalent to theoretical plate is a small. Then in that particular column, we have more number of theoretical plate. Therefore, height equivalent to theoretical plate is the height of theoretical plate in which or on which the single distribution equilibrium takes place. Therefore, in this case, this is the HTP. This is the height of single theoretical plate. If here solubility of this A and B is less in this stationary phase, sometimes this much area will be utilized by the sample component. At that time here, height of HTP is getting increased up to this. Therefore, in case of liquid chromatography, solubility, that is a factor, determines the height equivalent to theoretical plate or height of a theoretical plate. If that particular stationary liquid phase have a capacity to dissolve more solid, at that time maximum amount of solid is get dissolved into a small area or a small volume of the stationary phase. In that case, height equivalent to theoretical plate is small. Therefore, in that case, more number of theoretical plates are present in a small length of column. In adsorption chromatography, if number of functional groups on the stationary phase are more, then height equivalent to theoretical plate is a small. In case of liquid chromatography or in case of partition chromatography, when the solubility of sample component in the stationary phase is more, then smaller volume of stationary phase can dissolve maximum number of solid molecule. In that case, the height equivalent to theoretical plate is small. If height equivalent to theoretical plate is small, then more number of theoretical plates are present in the column. And if height of single theoretical plate is larger one like this, then that column consisting of less number of theoretical plate. Therefore, HTP, height equivalent to theoretical plate, determines the number of theoretical plate present in the column. Therefore, here the height equivalent to theoretical plate, number of HTP can be determined by this formula. Here L is length of column upon height of single theoretical plate. Height of single theoretical plate. Therefore, number of HTP, that is L, is equal to length of the column upon height of single theoretical plate. If theoretical plate have a smaller height, then that column consisting of more number of HTP. If height of single theoretical plate is more, then that column consisting of less number of HTP or less number of theoretical plate. The height equivalent to theoretical plate depends upon number one, number of functional groups present on the stationary phase. If it is a adsorption chromatography, or sometime here solubility solubility of sample component in a stationary phase if it is a partition chromatography. That means here, if number of functional groups on the stationary phase are more, then smaller area is required to form a particular distribution equilibrium. In that case, height equivalent to theoretical plate is very small. Therefore, here number of functional groups are more, then size is small, and number of HETP in the column is more. In case of partition chromatography, if minimum volume of that particular liquid is required to dissolve that solute, then a more number of theoretical plates are present in the column, or a height equivalent to theoretical plate is small. Therefore, in case of partition chromatography, solubility determines the height of theoretical plate, and in case of adsorption chromatography, number of functional group determines the height of single theoretical plate. Therefore, here height of single theoretical plate that depends upon the number of functional groups and solubility of the sample component, but here length of the column is also governs the height equivalent to theoretical plate, number of a theoretical plate. Here, if length of column is more, then more number of theoretical plates are present in that particular column. And if length of column is small, then a number of theoretical plates in that column is less. But here, for a fixed column, if height equivalent to theoretical plate is small, then the number of theoretical plates in the column are more. If this is the height, therefore here for this small length column there are 4 theoretical plates, and for that same length of this column there are only 2 theoretical plates. Therefore, smaller the height, more number of theoretical plates are present in the column, and number of theoretical plates in that particular column that can be increased by increasing the length of the column. If we increase the length of the column, then we have more number of theoretical plates in the column. In this case, if we increase the length of the column, then also theoretical plates are increases, but number of theoretical plates in this column are less compared to this column. That means here height of single theoretical plate determines the number of height equivalent to theoretical plate or theoretical plate present in the column. If column have more number of theoretical plate, means that column undergo more number of distribution and redistribution equilibrium. If column undergo more number of distribution equilibrium, then it has a more efficiency of separation of sample component. That column have a capacity to dissolve, to separate more components from each other. Therefore, efficiency of chromatographic column depends upon the number of theoretical plates present in the column. If column have more number of theoretical plates, then efficiency of chromatographic column is more. Efficiency means capacity to separate. Therefore, particular column have more capacity to separate 2 or more sample components if number of theoretical plates in that column are more. More the theoretical plate, more is the distribution or redistribution equilibrium, and more is the efficiency of separation of that chromatographic column. On the basis of this, we can also discuss the resolution of 2 sample components in the column. Suppose, for example, we have 2 two component A and B. If we pass this A and B, here distribution in mobile phase, and here a length of column. Suppose for example we have this much length of the column, and if we place two components A and B, here both A and B are present on the same position into the column. Because here column does not have capacity to resolve, to separate these two from one another. Therefore, both components are present over one another. If we increase the length of the column, then suppose for example this is component A, and here this much length, and this is component B. Therefore, some amount of this is a A and this is a B. But here some amount of B is present, here some amount of A is present. In such a case, we have the graph, or we have this resolution in this fashion. This is A and B, this is A and B. Here this is overlapping, means here this is not get separated, this is not get resolved. Therefore, if we increase the length of the column, then here this is a component A and this is a component B, A and B. Therefore, here is A and here is B. Therefore, A and B are get separated from one another. And if we increase again the length of the column, then here is position of B and here is position of A. That means A and B are get well separated from the one another as the length of the column is increased. Therefore, here this column has a poor resolution. That means efficiency of this chromatographic column is less, or it does not have efficiency to separate these two components from one another. Because A is mixed with B, and therefore this column does not have a capacity to separate these two components. Therefore, efficiency of this column is 0. Here this column have little bit more efficiency as its length is increased, but it does not separate two components. Here resolution takes place, though here some amount of A and some amount of B are mixed with one another. Therefore, as length is increased, the separation is get increased. And here this is a next column which have a component A is here, component B is here. That means here two components are get well separated. That is called as a resolution. When two or more components are get well separated from one another, then that column have more resolution. Resolution of chromatographic column, or you may say efficiency of chromatographic column, that would be directly proportional to length of the column. Resolution of chromatographic column or efficiency of chromatographic column is directly proportional to number of theoretical plates present in the column. Why this column have more resolution capacity? Because it consisting of more number of theoretical plates compared to this column. Therefore, number of theoretical plates in the column, that would be directly proportional to the resolution of two or more components. Therefore, resolution in chromatographic column or separation efficiency of chromatographic column is related with length of the column or the number of theoretical plates present in the column. Student, based on today's discussion, you can find out the answers of following question. What is theoretical plate? What is height equivalent to theoretical plate? How number of theoretical plate or number of height equivalent to theoretical plates are determined, and what is the effect of the theoretical plate on the separation or resolution of sample component? How efficiency of chromatographic column changes with the number of theoretical plate? You can find out the answers of this question In forthcoming lecture, we will discuss the different types of chromatographic technique. First is column chromatography, after that paper chromatography, thin layer chromatography, ion exchange chromatography, gas chromatography, and a high performance liquid chromatography. With this, we stop here. Thanks for joining me. Keep learning. Happy learning.